Okay, so there have been some changes. I got an email and Kate was on campus. The homework that was due today is about to Wednesday. We're going to talk about it some here to help you get completed correctly. And I've changed some assignments, some of the problems for chapter 4. And there will be a test on chapters 3 and 4 on the Monday before Thanksgiving break. And then we just have 1 week of classes after Thanksgiving before finals week. And we'll use that to review. Okay, so let's just to complete some things that we were working on. Remember that we had noted an equation of this sort where an operator acting on a function produces a constant times that function. And this is called an eigen problem, an eigenfunction problem, an eigenvalue problem. And the set of eigenfunctions depends on the operator. Each operator has a different set of, possibly different set of eigenfunctions. And so these are called the eigenfunctions. Set of them. Each eigenfunction has an eigenvalue. Sometimes there can be many functions with the same eigenvalue. That's possible. That's called degeneracy. And so, anyway, this is an example of this. So let's suppose we have that state, that particular eigenstate. We go to find, for example, the ensemble average, this operator, with the state, that particular one of the eigenstates. So what does this give? Average, in your case, average eigenvalue. Yeah, that's right. This gives a constant a times the wave function, and that constant can be pulled out of the interval. And this is in the interval over the probability, you should get 1. So this is just a. So the average of observations, average of measurements of whatever a corresponds to, should come out to be little a. What do we do? A squared. That's right. Everybody see why? Just operating with a twice, operator a twice. So in other words, looking up here, let's evaluate a operator squared on 5. The first one just gives a little a. The constant will, this operator doesn't act on the constant, passes through. And this one gives little a, so it just gives a squared. So how about the uncertainty? Zero. An eigen, if we prepare the state and an eigenstate of that operator, then the ensemble will be a narrow distribution, it has no width to it. Everybody comes back to the same value. Everybody reports back little a. Right? So if the state is prepared in an eigenstate of a, then the uncertainty associated with that measurement is 0. Standard deviation. Yes.
So this a hat, this average of the a hat, that's implicitly including phi sub a within that bracket. Those straight short brackets.
Not sure what you mean. This is what we've been using, right? The ensemble average for an operator is the wave function with the operator sandwiched between. And integrate over that.
How can you have an average of an operator?
It corresponds to a measurement. So the operator has a measurement that it corresponds to, and so this means the average of the ensemble of that measurement. So every measurement, every measured observable should have associated with it an operator that extracts the measured values. To get the ensemble averages, we perform this function.
What's a measured observable?
Oh, like X and P.
Is it something you can measure and you can see?
Yes. Something you can measure, you can't see it directly because we're talking about measurements made on atoms.
Fields count as one?
You can measure fields. Usually you measure the influence of the field on, say, the particle position. So that's how you measure field strengths.
So you actually can say the ensemble average of A hat, so that there doesn't have to be anything else. You actually have an average of an operator. So you're taking the average of the operator, how it acts in the entirety of the ensemble.
Correct.
So
this is the prescription for finding ensemble averages of a particular measured value.
So it would be wrong. Would it be wrong if we say A hat by A? So that A hat by A. Yeah, would it be wrong to put by hat now? Would it no longer be true?
Well, it's not the notation, right? The notation is this is defined as this. The average of anything, any operator over the ensemble is taken by inserting the operator in between the wave functions in the center.
This is only true for quantum mechanics.
This is specifically quantum notation.
Okay. This is not like math.
I can't say you're never going to see it anywhere else.
Yeah.
In any other circumstance, I don't know why you would want to say that. In the context of the quantum class, this is what this means. Okay.
By A is just give you the wave function.
It is the particular wave function that the ensemble has been prepared in. If you prepare the ensemble in an eigenstate of A, then all measurements will yield little a. Okay, so if you prepare the ensemble in by A, then all measurements associated with this observable will give the same value. What? Okay.
So each member of the ensemble?
Yes. Right.
They'll give the average.
Yes.
It won't give the actual its own members value, but it gives the average of the ensemble. Each member gives the average of the ensemble.
Right.
Okay, good.
Okay, now let's suppose we have a pair of operators, A and B. Let's suppose that they commute. And according to what I said last time, there is a set of operators, a set of eigenfunctions that are eigenfunctions of both operators, but with different eigenvalues. We indexed the states according to both eigenvalues. Over here, we index the state according to the eigenvalue for that operator. When we have two operators, we can form a set of states which are eigenfunctions of both at the same time. Yes.
So does a commutator say that this function forgive me, I didn't formulate my head, but like, is it saying that basically both A had Andy had solved, not solved, but like
The question in there somewhere, but
Yeah, I'm trying to think.
they're not coming up to the surface yet. So as an example, I did the simple harmonic oscillator. I had the Hamiltonian and the parity operator. And we saw that the eigenstates of the Hamiltonian could be, in fact, are also eigenstates of the parity operator. They're even or odd functions. So that would be an example, two operators. And the measurement of H corresponds to the energy of the state. Measurement of this of the parity operator would be whether it's even or odd function. Make sense? So for the example was for a simple harmonic oscillator. These were E sub n. We had a parity operator. We found the alternating sign plus minus plus minus plus minus as you go up the spectrum. Starts off even, next one's an odd function, it's even again, odd, odd. So n was going from 0, 1, 2, 3. And E sub n plus a half times H bar. Okay, so that's an example. Okay, so now applying what we just discovered here, the uncertainty with respect to A is 0, and the uncertainty with respect to B. How do we do that? Again, we make an ensemble, all prepared in the same way, in one of these eigenstates. And we have half of them out to half of the people are going to measure A. Take the other half, hand them out, everybody's going to measure B. And we find out that in the first half, we're measuring A. Unless first half that are measuring A, everybody gets the same value, little a. And the second half, everybody gets the same value, B. And 0. So if the two operators commute, then the product of the uncertainties can be made 0 by suitably picking state, which is an eigenstate of both operators. Yeah.
This is not bounded by one man's measurement. This is bounded by multiple men's measurements.
Ensemble effect.
Ensemble effect.
Each measurement is made only on one system. Each system has only one measurement made on. Half of the ensemble has been handed over. But this side of the class measure A, this side of the class measure B. But I started off making all of them from the same state. Okay, but we had an example. Of a pair of operators that don't commute. And then you remember the Canard uncertainty principle. We do the same thing. It means that we cannot find a set of eigenfunctions, which are eigenfunctions of both x and p. There is no set. There's no set of functions which are eigenfunctions of both. And therefore, the product has a lower bound, which is the Canard uncertainty. And he shows in a chapter later in the book that, in fact, in general, if you have two operators that don't commute, the right-hand side here is evaluated in terms of the commutator. I need to look up the exact expression. So in general, if you have two operators that don't commute, some other operator, then the lower bound is going to be related to this operator. That's called the generalized thing. Let's see, I have to remember this. I'm not sure that this is right. I think it's minus I over 2 times the ensemble average of C. So this catches both of these cases here. If C is 0, if the commutator is 0, then you can make the combined uncertainty to be 0. In this case, C is just a constant, and the average of the constant would be h bar over 2. I'm sorry, I h bar here, and so we get this in this case. So this is the generalized NR uncertainty principle. We proved it for the case of X and P, but there's a general expression for any two operators that don't compute. We have the same kind of result happening, but the combined uncertainty is a lower bound, depending on what this comes out to be. Questions? So this is the one you should remember, but it's a general, we're finding that there's a general kind of result. And again, it all depends on the algebra of the operators associated with this thing. It comes back to the mathematical structure of the commutation relation between the operators. Questions about that?
Yeah, so this is relating any two measurements, two separate measurements to the ensemble.
Yes.
This will always be
Yes.
true long as they're independent of one another. Or not independent, but sorry. So like if I measured like I don't know, like temperature or temperature in the acceleration or
Yeah. You're measuring energy, right? We measure energy of particles. We don't in this idea of having a single particle moving in a simple harmonic oscillator, you just measure its energy.
I'm just trying to understand what's different from the generalized Canard uncertainty principle versus the Canard uncertainty principle.
It's generalized to other operators, other measurements, other than just X and P.
And so what measurements would that?
For example, the energy imperative. Yeah. We're still talking quite generally about measurements, so we haven't really gotten down to how our measurements made. But generally, we have a means of measuring the position, the momentum, the energy, things like that.
What's another like real quality, or what's a real like property? Another real property that it works valid for.
The dipole moment.
So if
You have a compound system of positive and negative charge. Measure the electric dipole moment. Measure the angular momentum. Measure the magnetic dipole moment. So when we get to the hydrogen atom, electron will have an angular momentum in its orbit around the proton. You can measure the angular momentum. Some parts of the angular momentum could be measured. So we'll talk about that more. Okay, then there's another theorem. Again, starting with an ensemble average of some operators. Every measurement has associated with it in quantum mechanics an operator that describes the interaction of the system with some kind of measurement device. So we'll talk more about how to do that. That's coming. And he shows the time dependence of this ensemble average can be written sum of two terms look like this. And he gets this from Schrodinger equation. So if I take the top derivative of this thing here, there are three pieces in here inside the integral that can be time dependent. Psi star can have a time dependence. The operator itself can be time dependent. No, often it's not, but it can be. And then psi. Remember the time derivative of psi. Given by the Schrodinger equation, the time dependent Schrodinger equation, where I pull the constants over here on the right. So I just have time derivative. And similarly, there's a equation for psi star has the opposite sign here. It's a complex conjugate of this equation gives this. So when you take this time derivative here, you get the derivative of psi star, which gives you this, and then the derivative of psi. You also get the time derivative of both. So you would have psi star times the time derivative of O times psi, which is this, the expectation of derivative of O. And then you get this thing here, the commutator, H with the operator. The reason for the commutator is that first H is acting on psi star over here. And then the next time it's acting over here. And you get a difference because there's a sign. And that gives you the commutator of H with O. So for the details of the derivation, I want you to go read the textbook carefully to see the steps, but it all just comes about because of the Schrodinger equation. It's this result using the Schrodinger equation that gives the time dependence of the wave function. So here, the time dependence of the wave function is given by the Hamiltonian acting on the wave function. So we can also see then the ensemble that the time derivative of the ensemble average is related to how the operator commutes or doesn't commute with the Hamiltonian. Okay, so remember this. So how do we understand this, the time derivative of this average? How do we go about it? How do we go about measuring? Okay, we did this, we know how to measure this. How do we do this? Yeah, so
I'm guessing it's not as simple as just measuring the time that you reported the ensemble for and then dividing it.
sure. But now we have to remember you can only make one measurement on each member of the ensemble. So it doesn't mean everybody wait 5 seconds and take a measurement and then wait another second and make another measurement and then divide by 1 second. Take the difference between your two measurements and divide by 1 second. Doesn't mean that. Because you're making two measurements on the same system. The act of measuring alters the system. We will see more when we get further into this. The act of measuring changes the state that it's in. The electron is very small, so any attempt to try to measure the position of the electron will disturb the state the electron is in. So you can't make two measurements on the same state. But that is, this does not have to do with what happens if you make two measurements on the same state. That's the importance of the Canard uncertainty principle, the way I was trying to make sure everybody understood. Canard uncertainty principle doesn't have to do with making two measurements on one state. So that it's not what is often said. So what do you have to do here then? You have to divide the ensemble up into halves. You do it after 5 seconds, you do it after 6 seconds. Take the difference and divide by 1 second. And then if that was too long, we'll make the difference a half a second, or a tenth of a second, hundredth of a second, until it converges. Difference, the ratio converges. The rate. Does that make sense?
Just in what?
I think it is. Certainly this theorem is in the book. That's part of your reading.
Variation of that, or can you explain the way you said?
Well, I'm not sure that he was over it again, but I'm reviewing it again for you, the meaning of this. To accomplish this, you have to make one measurement on each system, which means you have to do it at two different times, which means that one half is doing it at one time, the other half is doing it at a slightly different time. You take the difference. So that's what this means. And each one of these is an ensemble measurement. You never measure twice on any system. That's the key. Okay, so now we're going to apply this theorem. And we're going to get a very interesting result from this. So let's suppose we do a free particle. And we're going to measure x. Get the ensemble average of that x. So this implies that we have prepared it in some state psi. This doesn't depend on psi, right? This is true for any size. So I can just pick some psi. Free particle in state psi, measure x. So this is the time derivative of the ensemble average. And the way it works is what I just said. Half of you do it after 5 seconds, the other half does it at 5.1 seconds. Take the difference and divide by 0.1 seconds. Okay, so let's go and put this in here. And it's a free particle. So what's the Hamiltonian for a free particle? Just the kinetic energy. I'm going to bring out the 2m. There's no time derivative. X does not have an explicit time dependence, so the partial derivative of x is 0. No explicit time dependence in x as an operator. The operator has no explicit time. And you see, are you okay with me pulling out the constant here? Remember, if you have a commutator, p squared over 2m x, and the same thing as so I can pull out the factor 2m. This is a constant that passes through all the operators. So I can pull out 2m. And then I'm left with this commutator squared x. Okay, so how do we do this? We're looking for commutator p squared with x. We know the commutator between x and p. Now we have p squared. So let's write down the commutator of x and p. What is this?
Should be negative I squared.
Now,
The variation is in class.
oh, let's see.
Something in the homework where it was like p squared.
Yeah, this is correct. I mess up on the sign. Correct. And this is going to operate on a function. There's implicitly over here a function that this is going to operate on. So this gives minus I minus IH bar x d by dx. This cancels here, so I have the derivative of x with respect to x. And then I get this term is important, not to lose. If you remember, this is all acting on some function over here. So that's all that remains. If I didn't mess it up in the derivation
I thought it
class.
was just the p hat was like negative IH bar.
Yeah, that's right. There is a typo in one place in the text that negative sign, but not commutated. Okay, so let's do this. Let's write this xp minus px is equal to IH bar. So I'm going to pull out from this what happens if you switch the order. So if I have p on the left side of x, I can flip the order, but I have to add a constant. So what we want now is p squared x. What is this? This is p squared x. What happens if we flip the order of p squared with x? Well, we can do it in steps. We can do it in stages. Okay, so I want to push this x over to the left so that it will cancel that term. So if I rearrange this order using that expression, this is then p times x hat p hat plus okay, so I succeeded in getting x into the middle. Started off on the right hand side, now it's in the middle. I got to do it one more time. And apply it to that combination. Okay, then we write this out. Now this x hat p hat squared plus, now we have two of these IH bar p's. Okay, we move the x all the way over to the left. And now that will cancel with this. Commutator of p squared with x is just 2 IH bar times p. So let's go here. We wrote this as 1 over 2m times this. So now we have okay, and we oops, let's see here. Did I make it? Should be. Hang on, I do p squared with x. Oh, this is, I got rid of this wrong. This is negative here. That's right. I'm going to move this over here, so it's a negative over here. Sorry about that. Negative here. And again. So I need a negative sign here. Okay, and then when it all cancels out with this. That looks like. This is like a velocity here. Not a velocity of an individual system, but it's an average speed for the ensemble. But you have to do it by making measurements of x at 2 different times on different systems, right? They have to coordinate all these measurements so that nobody's doing double measurement. And then we have an ensemble average speed, so we have to make momentum too. So we have to divide the ensemble up into maybe 3 parts. 2 parts for this measurement, time derivative, and we need 1 part for this measurement. But this says then that the ensemble average of P, the momentum divided by the mass, is going to be the speed, the ensemble average speed, when we understand what we mean by ensemble average here, taking the time derivative. It's like Uridan flow. So there's something now we're recovering from the Schrodinger equation, something that looks kind of like the Newtonian mechanics. But everything is done through ensemble averages. Don't forget that. That's a really important point. That we have, this is true for averages. But it's true for any state, any size. Remember, in a pure mode, it's goes to 0. Remember that? Yeah. So there are cases where the ensemble averages aren't time dependent, so we should get 0 when we go through this. So the average momentum would be 0. Pure mode. Well, that makes sense. Yeah.
Does it need to have a free particle?
Have a free particle, there's no forces acting. Potential is 0 everywhere. So it's not being influenced by anything. Okay, so here's another one. Let's do the time derivative of the average of the momentum. What's the corresponding classical equation? Here's the classical equation. What's the corresponding classical equation for this? That should be equal to the force. We have a particle moving in potential. What's the force? If I know v of x, how do I get the force?
Well, if it's conservative force, it'll be negative, right?
We're only talking about conservative forces. So I should get something like an average of v prime, average force. Okay, so let's go through the same process again. Again, there's some, it's not written explicitly here, but there's a state associated with this. This means an ensemble average associated with some particular state, right? And then we get this, and then there's possibly another term, but there is no explicit time dependence to the operators, P. Okay, so we need to do this. Kinetic energy and potential energy together form the Hamiltonian. So this has 2 pieces to it. So I should be able to write this is going to be the same sum of the 2 commutations. Which you can check by just going back to the definition of the commutator. How about this one? What is this? K, this is K. P squared with P. Commutator P squared with P. squared times p is p cubed, and p times p squared is p cubed. Doesn't matter whether we do p and then p squared or p squared and then p. Same operation, you're taking three derivatives. Okay, so that one gives 0. We're left with this one. Let's write that one down. Okay, it's important to remember, I have stopped writing that this thing is acting on a function. It's implicitly, when I'm writing an algebra, when I'm writing an operator equation, I haven't written down the fact that this is going to operate on some function. So right here, this derivative is acting on everything to the right, which includes another function out here somewhere, right? Okay, so in other words, we have this term times some function, could be some wave function. How many terms are present here? There's 2. D prime of x times psi plus b of x times psi prime. Right? So when I write this, I have to keep that in mind. There's actually 2 terms, whereas there's only 1 term here. This derivative is acting to the right. That's this one. And now I have 2 terms here that I have to write down. I h bar b prime of x psi plus I h bar b of x derivative. Acting, so I'm not writing psi, right? This thing is going to act on the function. Right. And there's 2 terms here cancel. So the commutator of the potential energy with P is the derivative of D. So d by dt of the expectation value, the ensemble average, I over h bar times I h bar and the average D prime. Which is the average of negative of B prime, which is the average force. This is true for any state and its potential. So it says, again, how do we go about doing this? Well, we prepare it in one state, but then I give it to 1/2 measured at 5 seconds, and I give it to another group that measures it at 5.1 seconds. Take the difference between those 2 groups, divide by 0.1. I think that's what that means. So if I do that, then the rate of change of the average momentum is related to the average force acting over the ensemble. That means I also have another group ask you to tell me what is the force acting on part. And then those will be equal to each other. So we're making some connection back to classical mechanics. And it's very tempting to figure out, can we complete that kind of connection? What is the connection we should expect between quantum mechanics and classical mechanics? And that's the subject of, I think it's chapter 7, which we'll cover next semester. But the gist of it is the following. You always have to remember that you're doing in quantum mechanics ensemble averages, which means that you have to compare to classical systems also done in ensembles. We're used to doing classical systems one at a time. But to make a comparison, you have to compare apples to apples. Because quantum mechanics is always ensemble. You have to do the same thing classically. Which means that we have to be making measurements on ensembles of classical systems. And when we do that, we find there's a very interesting close connection between the two, and that's really the way to make what's called correspondence between quantum mechanics and classical mechanics. You can start to see the what exactly are the quantum effects? Some of it has to do with that we're always dealing with ensembles, so you don't want to get that confused. That's not really a quantum effect. The fact that we're dealing with a theory that can only do ensembles is not a quantum effect. That's to do with the structure of the theory, the way the theory is set up. So we have to compare a classical ensemble theory to the quantum ensemble theory. Find out exactly what are the quantum effects. And that's what's done. And most textbooks do a lousy job of this. And this book does a much better job. Okay. Any questions? Yeah, you have to be careful about this, what this means. Let's go back to that. It means that the operator itself doesn't have explicit time dependence. So an example, X and P have no explicit time dependence. The operators don't. An operator that could have an explicit time dependence would be suppose the potential energy dependent on time, for example, which you could do by, say, if it's a simple harmonic oscillator, let's suppose you're changing where the spring is anchored. So if you had a post like this, but you could oscillate the post, then the potential energy becomes time dependent because the potential energy depends on the stretch of the spring. You're changing the other end of the spring. So now there would be an explicit time dependence in this case. Another case would be if you have an electron orbiting a proton, you have an electric field. So the hydrogen atom is inside of an electric field. If the electric field is oscillating, changing in time, then the potential energy associated with the electric field acting on the electron would be time dependent. And so in that case, you would have things, you might have something like this. That's not zero. That would be an example. So in all the cases we considered, this term is going to drop out. Like if it's just momentum operator or position operator, there's no explicit time dependence in the operator. Does that make sense? Because it's
because this is not for free particles, this is for anything.
Yeah.
It's,
anything with moving in a conservative force.
but can you not make it explicitly dependent on time?
Sure. Can you not make the potential explicitly dependent on time? Yes. I mean, that's particle in a box or the simple harmonic oscillator, the potential isn't dependent explicitly on time.
But you could though, right?
Sure, you could, and here's a way to do it. Or the particle in the box, you move the walls. So you can have some explicit time dependence going on.
So would that be generally, so I'm confused why we make that go away then.
Well, not dv dt, this is always zero. But if you have a term like dv dt, potential energy, so you have the time derivative of the potential energy of the ensemble average of potential energy. For example, in that case, if the potential energy has an explicit time dependence, that term has taken into account.
So we're making an assumption that the p hat operator doesn't exist.
Well, it doesn't. It doesn't. It's just the time derivative with respect to x. There's no explicit time dependence in that operator. Right? Just taking the derivative of the wave function. The wave function may depend on time, but the operator, the derivative operator, doesn't depend on time. I'm take the derivative with respect to x in the same way at all times. Say
That's true still, isn't it? correct. If you literally take the time group that. Yeah, for the 0. So it's just understood in reference, it's still not understood in reference to where it's the wave function. Said earlier. That's what-
Not the wave function, the operator. The operator, does the operator have explicit time dependence? That's what, this was the general theorem, and the meaning of this term is to have explicit time dependence in the operator itself. Whereas X and T have no explicit time dependence. Hamiltonian often has no explicit time dependence, but it can. For example, if something is happening to the potential energy in a time dependent way. For example, I can take the particle in a box and move the potential walls. I can move the walls in and out. Then there's an explicit time dependence to the potential energy. Or an electric field, oscillating electric field acting on a charged particle. That would be an explicit time dependence. Potential energy itself, or the Hamiltonian. Okay. All right, so this homework is due Wednesday, one of the day. And